Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Organic Chemistry, Paper 3. In the Unit 3, we are studying about heterocyclic compounds. In Lecture 4, we are going to study about synthesis of 5-membered heterocycles. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. Let us look at the topics that will be covered in this session. We will start with the general reactions leading to the formation of heterocycles. So, we will focus mainly on ring closure reactions by nucleophilic, electrophilic and the cyclic transition states. Then we will study about what are the key reactions and what are the important reactions that drive the driving force for many of these cyclizations we will study, and we will also study about the various reactions of Furon, pyrol and thiophane synthesis. Some of the name reactions include Paul-Knorr synthesis, phased Benari synthesis, commercial Furon synthesis, Knorr-pyrol synthesis, Hans-pyrol synthesis and Hinsbeck reaction. The Hinsbeck reaction is mainly used for the synthesis of thiophanes. Welcome to the next session. In this session, we will be studying about synthesis of 5-membered heterocycles. In the beginning, we will look at what are the general methods of synthesis of heterocycles. So, there are major types of reactions we will be looking at. The first one is intramolecular reactions. So, here the functional groups are mainly present at the terminal. Some of the examples include Paul-Knorr method, Fischer-Indol synthesis, Bischler-Napierski reaction, radical cyclizations and Asavitic reactions, and many of these reactions we will be studying in this particular session and in the future sessions also. And the next major type is the cycloaddition reactions. So, here some examples include Knorr-pyrol synthesis, phased Benari-Furon synthesis, Diels-Alder reactions, Combs synthesis, etc. And the combination of these two, that is the intramolecular cycloaddition reactions, are also used for the preparation of heterocycles. One such example is 1,3-dipolar addition. So, these are all the major types of reactions by which heterocycles can be prepared. Of course, when the reaction occurs, there should be some driving force for the reaction to occur, and we will be looking at some of the important driving forces that are very crucial for these kind of heterocyclic reactions. One is whenever there is a elimination that is possible, the elimination generally proceeds in the direction that leads to aromatization. So, in other words, what we can say is, if there is a possibility of an aromatic product that is being formed, then elimination generally proceeds in that direction. Examples include Paul-Knorr synthesis, Gomes synthesis of quinoline. These are some examples of these reactions. When we study about this reaction mechanism, we will understand how the elimination actually directs the product formation towards aromatization. And when in the case of 5-membered rings, the double bond rearrangement leading to aromatic system is also another important driving force. The main thing what we have to remember is, whenever there is a aromaticity or aromatic nature that is being formed in the final product, that actually gives stability to the product. So, that is one of the crucial driving force for the reaction to occur. So, in the case of double bond rearrangement, we can actually look at Knorr-pyrol synthesis. When we study this reaction, we will see how the double bond migration leads to aromatization, and that is the driving force for the product formation. And we also have other reaction, tautomerism reaction. Here again, the main important thing is the formation of aromatic systems. If you look at 2-pyridone, the 2-pyridone undergoing tautomerism to form 2-hydroxypyridine is a very important reaction. This pyridine moiety is actually an aromatic system, whereas the pyridone is not an aromatic system. So, the driving force for this particular tautomerism is the formation of aromatic system. And also the oxidation of dihydroderivative to aromatic system is another important reaction. So if you look at all this reaction, the final step or the formation of aromatic system is a crucial reaction, and that can be formed by different types of reactions. Say for example, in one case the aromatic system is formed by elimination reaction. In other case, it is a double bond rearrangement reaction. In some other case, it is a tautomerism, and in few other cases it is the oxidation reaction. So the reactions may be different, but the end result is the formation of aromatic system. Let us look at some major class of reactions or the type of reactions by which a heterocycle can be formed. If we talk about a 5-membered heterocycle, there are 4 carbon atoms and 1 heteroatom is present in this particular system. So the simplest approach is actually the 4 plus 1 approach. That means 4 carbon atoms come from one substrate and the heteroatom comes. So these two combine together to give a 5-membered heterocycle. When we extend the same for the 6-membered heterocycle, it is going to be 5 plus 1 system. So 5 carbons come from one unit and one halogen, the one heteroatom comes from outside or from other substrate. So that is how we have another approach, which is a 5 plus 1 approach. Basically, when we talk about 4 plus 1 or 5 plus 1 approach, we mainly use dicarbonyl compounds and the heteroatom. Polymer synthesis and other synthesis are examples of this one. So when we study about the polymer synthesis, we will see how the dicarbonyl compound and one heteroatom can be converted to the heterocycle. And there are also other approaches in which we have a 3 plus 2 approach, because the number 5 can be formed as 4 plus 1. This is one combination, and we also have 3 plus 2 combination, which leads to 5. So here in this case, there are 3 carbon atoms from one particular substrate, and the heteroatom and another carbon comes from a different substrate. So these type of reactions are called 3 plus 2 approaches. And when we talk about the 6-membered ring approach, it is basically 3 plus 3 approach. So these are all the different types of reactions by which heterocycles can be formed. Now let us look at some of the important reactions which leads to the formation of heterocycle. The first and foremost is the nucleophilic ring closure. So here, formation of a acyclic starting materials, that means the final product is formed from acyclic starting material. That means as we have seen, the 4 plus 1 approach or 5 plus 1 approach is an example for this one. So here we have a starting material which is a acyclic system, and that leads to the cyclized product. So one such example for nucleophilic ring closure we will see soon. And another one is formation from lesser ring. That means one carbon less, or maybe there are a couple of other ways by which we can form. If we have a 5-membered or a 6-membered ring, there is also another 5-membered ring with the heteroatom is formed. So in this particular case, a bicyclic, that means we have ring 1 and ring 2, 2 ring systems are there. This can be formed from a monocyclic system. Say for example, we can start from the aromatic system, and we can actually add this heteroatom, and with this we actually form the cyclized ring. So that is what is the another example in which a bicyclic ring is formed from a monocyclic ring. So this is another example of a nucleophilic ring closure. We also have electrophilic ring closures, and we will also look at why the nucleophilic ring closure is the most preferred reaction compared to electrophilic ring closure, we will see. And there are also other reaction, but by means of cyclic transition state, that also leads to ring closure. Then we can also convert one heterocyclic ring into another one, and we can also modify a existing ring. So these are all the major reactions by which heterocycles can be formed. So let us look at the nucleophilic ring closure, or which is the most important reaction for heterocycle formation. So here, reaction of two halogen or acyl halides with the The heteroatom and the hydrogen, these are the different starting materials which are involved in the formation of the nucleophilic ring closure. So, when we have the halogen atom at the terminal or maybe the acyl halides at the terminal with the alkyl chain, and we have the heteroatom that is going to be involved in that heterocyclic ring formation. When these two react together, the hydrogen and the halogen atom combine together to form HX as the byproduct, and we get the cyclized product with the alkyl chain. R is the alkyl chain, this is present in the starting material. So, the heteroatom now joins with the alkyl chain to give the cyclic product. So, this is one type of reaction. So, in this reaction, the halogen or the acyl halides are generally present at the terminal place. And there is also another reaction we talked about, which is the polymer synthesis. In this, we talked about the dicarbonyl system undergoing the reaction. So, the terminal carbonyl units, that means we have two carbonyl units which are present at the terminal, which is connected by a alkyl chain, and this is again reacted with the corresponding heteroatom. Means if it is the heteroatom is nitrogen, then we will have actually ammonia. This is NH plus H2, that is actually ammonia is the substrate, and we can also have oxygen and sulfur systems in this particular case also. So, the dicarbonyl compounds can undergo cyclization, nucleophilic ring closure to give the corresponding heterocyclic compound. If the carbonyls are separated by 2 carbon, that means if they are 1,4 dicarbonyl compounds, we get a 5-membered heterocycle, and if they are separated by 3 carbon, that means if we have a 1,5 dicarbonyl starting material, we end up with a 6-membered system. So, these are all the different ways by which diketo compounds or dicarbonyl compounds can be converted to heterocycles. Here, as we mentioned, the ZH2 may also be in some cases a amino group. When two heteroatoms are required for the formation of the heterocyclic ring, we can actually use hydroxylamine, hydrazine, hydrogen peroxide. These all can be used. When we use hydroxylamine, nitrogen and oxygen are the two heteroatoms which will be included in the ring, and when it is hydrazine, there are 2 nitrogen atoms that are involved, and when it is hydrogen peroxide, it is 2 oxygen atoms that are involved. So, let us look at the next type of cyclization reaction, that is a electrophilic ring closure. Because we already know oxygen, nitrogen and sulfur, all these three are actually nucleophiles because they have lone pair of electrons, and that is the reason they generally cannot participate in the electrophilic ring closure reaction, because they cannot act as a electrophile. So, in these kind of cases, what happens is we have to have a aromatic system, which is very essential for these kind of electrophilic ring closures, and the corresponding heteroatom is generally present outside the ring, and that is the reason we mentioned here the electron rich aromatic ring is a prerequisite, because this can only react with the electrophile. So, here is a example of the alpha beta unsaturated compound. So, this is the electrophile which will undergo reaction with this particular aromatic ring, and these type of reactions, basically anilines, phenols and etc. are mainly used for the cyclization reaction. If we start with aniline, that is with the nitrogen starting material, we end up with a quinoline unit. This is nothing but a quinoline ring. So, the nitrogen is present in the next ring. So, this is also another example of addition of one more heterocyclic ring formation. We can also consider this as an example for that reaction. The next one is the cyclic transition state reactions. So, the ring closure occurs during the cyclic transition state. Diels-Alder reaction is the most important reaction of this particular type, and here The heteroatom may be present in the dienophile or it can be present in the diene part. So, the heteroatom can be present either on diene or on the dienophile. That leads to the cyclic system. So, during the cyclic transition state, this reaction actually proceeds, and this is an example of ring closure. The next type of reaction is the conversion of one heterocyclic ring into another one. Here we have a oxygen heterocycle. So, this oxygen heterocycle is converted into oxygen and sulfur heterocycle. So, this is basically carbon disulfide when reacted with an epoxide in the presence of sodium hydrate, that is a base, leads to the formation of this cyclic system. And here the ring expansion actually takes place. As we see here, this is a 3-membered starting material which is converted to a 5-membered ring material compound. So, that means this reaction occurs through ring expansion, and in some cases rearrangement of ring atoms are also possible, and we can also have ring expansion or ring contraction which can be carried out photochemically. So, these are all the various ways by which one of a heterocyclic ring is converted to another. So, in this particular case we have the tetrahydrofuryl alcohol. So, this is a 5-membered ring. This when treated with ammonia is converted to a 6-membered pyridine. So, that means one heteroatom, that is oxygen, is replaced by another heteroatom, nitrogen. So, this is also possible in the case of ring expansion, or this is an example of conversion of one heterocyclic ring into another heterocyclic ring. So, other types of reactions are modification of the existing ring, or examples of ring formation. What we can have is like intramolecular reaction as shown here. The nucleophilic system, that is the heteroatom, attacks the carbon having a good leaving group, that leads to the formation, cyclic system formation. This is one type of reaction. And also we can see dehydrogenation of aromatic heterocycles with sulfur or palladium catalyst leads to the formation of cyclic systems. So, these are some of the ways by which the reaction can happen. So, the attacking nucleophile and the leaving group can be present on either carbon, or it can also be present at so, when the nucleophile attacks the carbon, here it leads to the 3-membered ring formation. In this particular case, it leads to a 4-membered ring formation. Let us look at other few key reactions which we will be encountering. One is a Aldol reaction. So, here in this particular reaction, what happens is like the product, the reaction is carried out in the presence of a hydroxy derivative. So, this condensation leads to the alpha beta unsaturated system. This is one of the important preliminary reactions or the initial reactions in the formation of heterocycles. When we look at some of the examples, we will see how this reaction actually proceeds. And another one is a conjugate addition. This is basically a 1,4 conjugate addition. So, we have numbering like 1, 2, 3 and 4. So, when this reaction actually Michael addition is one such example. So, these kind of conjugate additions are also important reactions which are the initial steps in the formation of heterocycles. And we also have various base catalyzed condensation reactions. Some of the name reactions are given here: Aldol condensation, Novenagel condensation, Claisen, Diekmann, Claisen-Schmidt, Perkin and Henry are various base catalyzed condensation reactions, and all these reactions are involved in the heterocyclic ring formation in any of the steps. They may be in the beginning or they may be in say intermediate steps. For example, in the case of Aldol reaction, enol or an enolate is one of the substrate. Enolate ion is one substrate, and this is reacted with a carbonyl compound to lead aldol or a conjugated enone as the final product. Or when we have active methylene compounds, they also react with the carbonyl compounds in the presence of a base to give alpha beta unsaturated ketones. The condensation of esters with the esters or carbonyl leading to the formation of beta ketoesters or a beta diketone is called the Claisen condensation. When the same reaction happens intramolecularly, we call that as a Dieckmann reaction. Here we have a cyclic beta ketoesters as the final product. And Perkin reaction is a reaction between an acid anhydride and aromatic aldehyde that gives a cinnamic acid. So, these are some of the reactions which are generally used in the heterocyclic ring formation. So, here is one important reaction, that is EMain formation. So, this is quite often encountered in the heterocyclic formation. A carbonyl compound in the presence of a acid, that is protic acid, undergoes the addition of proton occurs on the oxygen atom, which leads to the oxonium ion formation, and all these reactions are basically equilibrium reactions, and these are in organic chemistry we call this as a microscopic reversibility of reaction, and these are basically elementary steps that are very, very crucial. So, once the oxonium ion is formed, we have a base, basically a primary amine, as shown here. R3NH2 is the amine. This amine has a lone pair of electrons, and this lone pair of electron, with lone pair of electron, it attacks this particular carbon, electrophilic carbon, and simultaneously this bond is shifted towards the oxygen. So, we end up with the positive charge of the oxygen is removed by the shift of this double bonded electrons, and the nitrogen, since it lost the lone pair, becomes a positive charged ion. So, this is the intermediate that is formed initially, and then there is a proton transfer takes place. Basically, in many of this reaction, a proton transfer is a very, very crucial step. That means one of the hydrogen from this amino nitrogen is shifted to the hydroxy group. Why this happens is basically OH is a very poor leaving group. So, to make the poor leaving group a good one, a proton simply adds to this particular hydroxyl group, that makes a H2O plus, and this H2O plus is a very good leaving group, and this leaves at that time, since when the proton is shifted, the bonded nitrogen hydrogen bonded electrons were given back to the nitrogen. So, there is a lone pair, and now this lone pair is coming between the carbon nitrogen bond with concomitant removal of water molecule. So, this is a very crucial reaction that leads to the formation of the EMain, and this nitrogen, which is having a positive charge, loses a hydrogen atom as proton. So, this bonded electrons are now given to nitrogen atom. So, we end up with the cis and trans EMains are formed. So, this is one of the crucial reaction. That means the starting material is a carbonyl compound. This carbonyl compound reacts with an amine to give the corresponding imino derivative. So, the EMain formation is very, very crucial, and in many cases this EMain formation is the crucial step for the cyclization. So, that is how many of the heterocyclic reactions proceed. Now, let us look at the detailed synthesis of furans, pyrrole and thiophanes. First, we will start with the synthesis of furon. This is a very simple method and a very old method. In this method, distillation of pine wood gives furan. So, mucic acid is a compound that is present in the wood, pine wood, and when we heat this one, when we heat this mucic acid at a very high temperature, this loses carbon dioxide molecule, and this also loses 3 molecules of water. That leads to the cyclic furoic acid as the product, and this furoic acid on further heating loses 1 molecule of carbon dioxide to give the corresponding to give furan as the final product. So, here this carboxylic acid unit loses the carbon dioxide. Let us look at a very important reaction, that is a polymer synthesis. So, this reaction actually involves dehydration of 1,4-dicarbonyl compound. That means, as we have seen, the dicarbonyl units which are present at the terminal are involved in this particular ring formation or the heterocycle formation reaction. So, the carbonyl compound may be dialdehydes or it may be diketones, and this reaction occurs under non-aqueous acidic conditions. So, this is very important, because if the reaction occurs under protic condition, that means under acidic conditions, that leads to the formation of in this particular case 2,5-dimethyl furon. Once we look at the mechanism, we know how the reaction actually proceeds. But on the other hand, if the reaction actually occurs in the presence of a base, then instead of the heterocyclic compound, we only get a carbocyclic compound, that is a 3-methyl cyclopentenone. So, in both the cases, water molecule is lost, but under the different reaction condition, whether the reaction occurs under acidic conditions or basic condition, the product distribution actually changes or the final product changes. So, that is the reason we have to choose the right condition for the heterocycle formation. And in this particular reaction, some of the steps involved are the initial formation of the enol tautomer of this dicarbonyl compound, and in the cyclization step, that involves the attack of the enolic hydroxyl on the electrophilic carbon atom. That means, basically between two carbonyl units, we actually form the enolic with the one carbonyl unit, and we will be having a hydroxy, because when it is formed as a enolic hydroxyl, there is a lone pair of oxygen on this oxygen, lone pair of electron on this oxygen. So, this attacks this electrophilic carbon, and that leads to cyclization. So, this is a very crucial cyclization step. And finally, dehydration of the hemiacetal leads to the final furon formation. So, let us look at what is the actual mechanism for this reaction. So, here is the mechanism given for this reaction. So, as we mentioned, the reaction actually proceeds in the presence of acidic condition. That means, H plus ion is very essential to initiate this reaction. As we have seen, in the presence of hydroxide or under basic conditions, we do not get the furon, which is a heterocycle, but we only get the carbocyclic system. So, this reaction actually proceeds, the polymer synthesis proceeds by the addition of a proton in the initial step. So, the first step is the protonation of the carbonyl carbon. So, there are two carbonyl units are there. We can actually choose, this molecule being a symmetric one, we can actually choose any one of the carbonyl group which undergoes protonation. So, this is the keto form of the starting material, and addition of a proton takes place in the initial step. That leads to this intermediate, and this loses a hydrogen atom as a proton, and that leads to the formation of enol. So, once the enol is formed, as we mentioned, this enol is a very crucial intermediate in this reaction. So, what actually happens is, there is a keto-enol tautomerism occurring in the presence of acidic condition, and once the enol is formed, in the next step, what happens is, the second carbonyl unit is now protonated by the acidic proton. So, due to this carbon becomes more electrophilic in nature. Now, a lone pair of electrons from this oxygen attacks the electrophilic carbon atom, leading to the cyclization. So, this is a very crucial step. The enolic oxygen attacking the carbonyl carbon, leading to the cyclized product, is the crucial reaction, and this leads to the hemiacetal as shown here, and there is a proton transfer, because one of the hydrogen from this oxygen is shifted to the hydroxyl oxygen. So, that leads to the formation of the hydronium ion, H2O plus ion is formed, and once a H2O ion is formed, this is a very good leaving group, and the loss of hydrogen leads to the concomitant loss of the water molecule, that is loss of hydrogen as proton. That means, the carbon hydrogen bond gets the bonded electrons directly from it. So, that leads to the double bond here, and finally, we end up with the furon as shown here. So, these are all the various steps that are involved in the Paul-Knorr synthesis, or this is the mechanism for Paul-Knorr reaction. But recently people had actually shown that there is no ketoenol tautomers as we have seen in the earlier one. So, here they have proposed a little bit a different mechanism. So, in this case there is no selective enol formation as the initial step, because they have carried out some unsymmetrical carbonyl compounds, and they have actually proved by spectroscopic technique that there is no enol formed in this reaction as an intermediate. So, there is a different mechanism proposed for this reaction. Of course, this reaction also proceeds in the same direction, that means addition, that is the protonation of one of the carbonyl oxygen happens at the initial step, and instead of a enol that is formed, this particular ion is actually attacked by the double bonded electron from the next carbonyl unit, and once the hydroxy, this tetrahedral intermediate is formed, which is having the hydroxy unit, this gets a proton, and that becomes a H2O plus, that is a hydronium ion, which can easily be lost. And the other steps are very similar, like the neighboring hydrogen is lost as a proton, and shift of the bond actually takes place, leading to the final formation of the furon. So, the overall steps, if you look at, there is no ketoenol tautomerism as mentioned in the previous mechanism, but the initial step is the same step, the protonation of the carbonyl. The last step is also the same thing, like loss of water molecule and proton. So, the first and last steps are similar, but only the intermediate steps there is a change. So, recently there are lots of improvements over the Paul-Knorr synthesis. Some of the modifications include 1,4-dicarbonyl surrogates are used instead of 1,4-dicarbonyl compounds. Epoxy carbonyls as shown here, or 1,4-diol-2-ines are also used as the starting materials, because these actually form, especially this diol, the alkyne diol actually gives the corresponding dicarbonyl compound in situ. And using this various substitutions, we can prepare various furon derivatives, and in most of the cases, as we say, the reaction is initiated by the presence of or the requirement of H plus ion. H plus ions are generally given by mineral acid. So, the mineral acid is used under aqueous condition to initiate Paul-Knorr synthesis. And if we use Lewis acid or a dehydrating agent, then we can actually use the same reaction under anhydrous conditions. So, they also initiate the same reaction. And when we have a unsymmetrical dicarbonyl compound, most of the time we end up with a mixture of product. What are all the different possible mixtures of cyclization that can occur? All those products are generally formed. And in some cases, the formation of the enol actually depends on the relative stability. So, that is also possible in some cases. So, selectively one of the product is formed based on whatever is going to be a more stable enol. So, here is another example of 1,4-dicarbonyl compound, that is a beta ketoester. Previously, what we have seen is, we have seen the dicarbonyl compound, that is a dialdehyde or diketones. Here is an example in which the 1,4-dicarbonyl compound is a beta ketoester, especially we talk about ethyl acetoacetate. Using this also we can prepare furon compounds. Various furon compounds can be prepared. One such example is given here. Here in this particular case, if we start from ethyl acetoacetate, we get 2,5-dimethyl-furan 3,4-dicarboxylic acid. So, this is the starting material, that is the dicarbonyl compound. This, when treated with iodine, loses 2 molecules of sodium iodide, and there is a condensation takes place between the central carbon atom. So, there is a intermolecular reaction that happens or that occurs between 2 ethyl acetoacetate units. and this can also be written as shown here. And now if you look at this is exactly the part which we are discussing about the 1,4 dicarbonyl unit. This is carbon number 1, this is 2, this is 3 and this is 4. So this is nothing but the 1,4 dicarbonyl unit which are generally used in the polymer synthesis. So now we know exactly how the reaction actually proceeds. We can follow the keto-enol mechanism or the other mechanism, and then once the enol is formed, this is treated with the sulfuric acid as a dehydrating agent, because this has to undergo dehydration. Sulfuric acid that is being used, that leads to the formation of the furon derivative. The next one is a phased Benari synthesis. This is a reaction involving a condensation. So here the condensation happens between, especially a deprotonated 1,3 dicarbonyl compound undergoes condensation with alpha halocarbonyl compounds. This is followed by cyclization or the ring closure, and in this case the beta dicarbonyl compound can be both ketones or a ketone and ester. So here we had given the example of a beta keto ester. So instead of the ester, we can also have a alkyl unit. That means this is going to be a beta diketones. So this reacts with the alpha halocarbonyl compound. So in the alpha carbon, we have a halogen unit that is present. So that is the reason this is a very crucial thing for this reaction. So an alpha carbonyl compound, alpha halocarbonyl compound and a beta diketone undergoes reactions in the presence of a base. So what is the role of a base? The base generally generates an anion on this active methylene carbon, because here these two protons are highly acidic in nature. So use of a base generates an anion, and this anion is crucial for the cyclization reaction to occur. So let us look at the mechanism and we will understand how the reaction actually proceeds. And this reaction actually prepares various substituted furon derivatives. So in the previous case, we were using the alpha dicarbonyl compound, that is 1,3 dicarbonyl compounds were being used, and most of the times, especially in the polymer synthesis, we were using only the symmetrical systems, that is symmetrical carbonyl compounds were used. So we cannot get different or substituted furon derivatives. But in this case, we have one alkyl group coming from the beta ketoester or the beta dicarbonyl compound, and another alkyl chain comes from the alpha halocarbonyl moiety. So that means we have more flexibility of getting different substituted furon derivatives. So this is the major advantage of using phased Benari synthesis. Let us look at the overall steps that are involved in this particular reaction. So the initial reaction is basically the condensation we talked about. It is the Knoevenagel condensation reaction. So that leads to the condensed product. So as we have mentioned, a base abstracts a proton from this particular carbon. So that leads to the formation of an anion, and this anion attacks the electrophilic carbonyl carbon. So as mentioned here, so that leads to the intermediate as shown here. This is the Knoevenagel condensed product, and in the second in the further reaction, the base abstract one of the hydrogen from this particular carbon. So there, once this particular proton is lost, a negative charge comes here, and that is being shared between the carbon and the carbonyl carbon. So we end up with a double bond on between these two carbons, and the negative charge which comes on this carbonyl carbon's bond now attacks. This is nothing but the internal SN2 type attack. So here is the nucleophilic site, this is the leaving group. So the backside attack actually takes place, leading to the concomitant loss of the leaving group. Here chloride ion is the best leaving group, and this is the intramolecular SN2 type reaction as shown here. That leads to the final product, which is the hydroxide derivative. and this hydroxide derivative has to undergo aromatization. So, this is what we have seen in the initial session, like there are few crucial reactions which are very essential for the formation of heterocycle. One reaction is the loss of proton leading to the aromatization of the product. So, here we have a hydrogen atom in this particular carbon. So, this is now lost and this water OH molecule is lost. So, these two combine together to give water molecule. So, the loss of water molecule leads to the aromatization of this particular moiety. So, that is one of the driving force for this reaction. So, the enolate is the crucial intramolecular displacement of the enolate. In other words, this is the nucleophile which attacks the halogen unit. So, this is the intramolecular SN2 type reaction. So, these are all the crucial steps involved in this phased Benari synthesis that leads to the final formation of a furon. So, let us recap what are the important steps involved in this reaction. The first one is the generation of the anion. This anion is basically generated on the methylene carbon. This is having the acidic hydrogen, because we have two electron withdrawing groups. That means, we have a carbonyl unit here and we have a ester unit here. So, both are electron withdrawing in nature. That makes this hydrogen, especially the hydrogen as shown here, more acidic, and this more acidic hydrogen can be easily abstracted by the base. So, this is one of the important step in the Knoevenagel condensation reaction. And the second one is the enolate ion attacking the alpha halocarbonyl derivative. So, this is the next crucial reaction. So, these two are the important reactions which are involved in the formation of the heterocyclic ring here. Let us look at some of the commercial furon synthesis. As we have seen, the pine wood or oats maize, these are all the easily available, commercially available starting materials, and when these are treated with either high temperature or with a strong acid, the oats maize when treated with HCl leads to the formation of different pentoses, and these pentoses on steam distillation with HCl leads the corresponding furfuraldehyde, and this furfuraldehyde when treated with calcium carbonate at a high temperature loses a carbon monoxide unit to give the corresponding to give furon as the final product. Additionally, this hydroxyaldehyde can also be treated with HCl, which gives a furfuryl alcohol, and this furfuryl alcohol on treatment with the calcium carbonate leads to the formation of methyl substituted furon. So, these are some of the commercial methods of preparation of furon and its derivatives. So, if you look at the mechanism for the previous reaction, that means from the maize, how do we get that? We have this pentose compound as shown here. We have a aldehyde unit and we have 4 hydroxy unit that is present in this molecule, and when treatment with the HCl leads to the loss of water molecule. So, one of the water molecule is lost. So, we have a enolic system formed in this particular reaction. So, since it is an enol, this undergoes keto-enol tautomerism, but of course, we know the ketone is the most stable one. So, that is the reason the enol very readily tautomerizes to give the keto derivative, and this keto derivative undergoes intramolecular reaction. That means, the lone pair of electrons on the terminal hydroxyl attacks the electrophilic carbon, and this leads to the formation of the cyclic derivative as shown here, and this terminal this carbonyl oxygen abstract the proton to give the corresponding hydroxy derivative, and the cyclization leads to this type of intermediate. So, there are two types of reactions which are happening here. So, one is the loss of water molecule in the first step, and then this loses carbon monoxide to give the furon as the final step. So, these are all the various reactions that are occurring in this particular reaction, and that leads to the final commercial synthesis of furon. So, let us look at the next type of reaction, which is synthesis of pyrol and thiophanes. The same starting material, that is the 1, 2, 3, 4, 1,4 dicarbonyl compound, when treated with the hydrogen sulfide or with the primary amine. So, these are all the two different starting materials which undergo reactions separately. So, this 1,4 dicarbonyl compound, when treated with the hydrogen sulfide in the presence of an acid, leads to thiophane. That means introduction of the sulfur takes place in this particular case. And if we use primary amine as the another substrate, the 1,4 dicarbonyl compound reacts with the primary amine to give the corresponding pyrrole derivative. Here the R group is present on the nitrogen. So, whatever is the substituent that is present on this primary amine, that is present here. So, we have a substituted pyrrole derivatives formed. If we look at the mechanism for this particular reaction, so we have earlier seen Polymer synthesis for furon preparation, and now this is a thiophane and pyrrole preparation. So, here the reaction is more or less similar to the one what we have seen, but the only difference is here in the previous polymer synthesis, the enolic oxygen attacks the carbonyl carbon to form the cyclic product. But in this particular case, what happens is this enol actually gets converted to the corresponding heteroatom substituted derivative. So, that is the major difference. So, initial step is the same, the protonation of the carbonyl oxygen takes place, and now this electrophilic carbon is being attacked by the nucleophile. So, whatever, whether we use hydrogen sulfide or ammonia, depending on either primary amine, if it is primary amine it is RNH2, if it is ammonia it is NH3, it is if it is hydrogen sulfide then the X is sulfur. So, we have different heteroatoms, the heteroatom may be nitrogen or sulfur, and this heteroatom now attacks the electrophilic carbon. And here in this particular case, once the nucleophilic system, that is hydrogen sulfide, ammonia or primary amine attacks this particular carbon, we have a 1, 2, 3, 4, we have a tetrahedral intermediate that is formed, and there is a proton transfer that takes place. That means one of the hydrogen from this particular heteroatom that was introduced shifts from here to the oxygen. So, that is the reason we end up with the H2O plus ion here, and this is lost as a water molecule. So, this is a very crucial step. So, this is the loss of first water molecule here, and once this water molecule is lost, we have the heteroatom that is present here, and this heteroatom there is a proton transfer takes place that leads to similar to the enol type material. Here we have a enamine or thioenol. If the X is nitrogen, we have a enamine that is formed, we have a en here and we have a amine here. So, this is the intermediate that is formed, and if the X is sulfur, then we have en and thiol. So, thioenol is formed. So, this is the crucial step, and now once this intermediate, either the enamine or thioenol, depending on what is the X, is formed, that undergoes the next cyclization, which is a very crucial reaction. So, these steps are already familiar with you. The heteroatom attacks the electrophilic carbon and the bond is now shifted towards the oxygen. That leads to the formation of the hydroxy derivative, or this hydroxy derivative undergoes basically the loss of water molecule. So, one of the hydrogen is shifted here and the OH is lost as water molecule. Then we end up with the corresponding pyrol or the thiophane derivatives. So, this is how the overall reaction, that is the mechanism for thiophane or pyrol, proceeds. So, if we start from the 1,4-dicarbonyl, if it is a open chain system, if it reacts with H3PO4, that is the acidic conditions only, we end up with the furon derivatives. If ammonia is also present or a primary amine is present, then we end up with the pyrol derivatives. And if it is a cyclic system with one of the carbonyl that is present outside the ring system, but if the compound has a 1,4-dicarbonyl unit, then use of concentrated HCl leads to furon derivative for the cyclized part. And if it is a primary amine, we end up with the corresponding pyrol derivatives. And similarly, that means from one membered ring, we are now going to two membered ring. That means the monocyclic ring is now converted to a bicyclic ring. And similarly, if we do the same reaction, that means the 1,4-dicarbonyl compound is treated with the hydrogen sulfide, we end up with the thiophane derivative. If we simply treat without hydrogen sulfide or without a primary amine in the presence of a concentrated acid, that only gives the furon derivatives. So, if we use ammonia or primary amine or hydrogen sulfide, that leads to the heterocycle with nitrogen or sulfur respectively. If we do not use either a primary amine or hydrogen sulfide, then we simply get the furon derivatives. So, the 1,4-dicarbonyl compound is the same starting material. Acidic reagents are also the same thing that are used, and depending on whether we use the second substrate, whether it is a primary amine or hydrogen sulfide, the product distribution, especially furon or thiophane or pyrol formation, changes. Let us look at nor-pyrrole synthesis. So, this is a condensation reaction between alpha amino carbonyl compound with the dicarbonyl compound. So, these are activated ketones. So, this activated ketones react with the alpha amino carbonyl compound in the presence of a strong base, gives the pyrrole derivatives. Here is another example which is shown here. So, depending on what is the starting material we are using, we may end up with the loss of water molecule to give the corresponding pyrrole derivative. We can have multi substitutions. So, in this particular case, we have 1, 2, 3 different alkyl groups are present in this particular different starting materials. So, we end up with the 3 substituted pyrrole derivatives. So, 3 alkyl substituted pyrrole derivatives can be formed by this nor-pyrrole synthesis reaction. So, the starting material ethyl acetoacetate is converted to the corresponding nitroso derivative. When treatment with sodium nitride in the presence of acetic acid actually gives the corresponding nitroso derivative. So, this actually exists as a oxime nitroso tautomers. So, these two tautomeric forms are actually possible, and then addition of one equivalent of saturated aqueous sodium nitrate actually leads to the formation of this particular intermediate. Then finally, the use of zinc dust reduces the oxime group to the amino derivative. So, here what we are doing is this alpha amino ketones actually generally undergo self condensation very quickly. So, we actually form this particular alpha amino ketone in situ starting from the corresponding nitroso derivative. So, this is our carbonyl unit, this is the ketone unit, let us say, and this is the nitroso unit, which is later on reduced to the corresponding amino unit by the zinc acetic acid reduction. So, what we have is basically the ketone is there, and in the alpha position we have the amino group. So, the alpha amino ketone is prepared in situ, and that undergoes the reaction to the final product. So, if you look at the overall reaction, the initial step is actually happening in the presence of a acidic reagent. So, the carbonyl unit is protonated in the first step, and this amino ketone, so this is the one which undergoes the reaction. So, how do we prepare this amino ketone? We have seen that. So, the starting the second unit of the ethyl acetoacetate. So, this is one starting material, because we are using two equivalent of the starting material. So, one ethyl acetoacetate is first protonated, and the second ethyl acetoacetate is converted to the corresponding alpha amino ketone derivative. So, how the reaction proceeds is, the second unit actually reacts with the sodium nitrite and acetic acid to give the hydroxyl this oxime derivative. This oxime derivative undergoes tautomerization to give the nitroso derivative, and this nitroso derivative can be reduced by zinc and acetic acid to give the corresponding amino derivative, and this is the amino derivative that is shown here. So, this amino ketone now attacks the protonated ethyl acetoacetate. So, here the proton transfer takes place, and we end up with the EMain formation. This reaction we already know how the EMain is formed from the carbonyl compound. So, once the EMain is formed, this loses proton and water molecule to give the ENamine. So, this is a very crucial reaction. So, we have a EMain, and the EMain is converted to the ENamine. So, this is the EN unit, this is the amine unit. So, both together are called ENamines, and this ENamine now undergoes the cyclization. So, this is the electrophilic unit, that is the electrophilic carbon. This is the electron rich nucleophilic system, that is the pi bond. So, this pi bond now attacks this particular carbonyl carbon, and that leads to the cyclization as shown here. And as we know, the hydroxy group can be lost as a water molecule. So, in this particular case, if you look at, we have two places from where the loss of water molecule may happen. So, as we have seen, whatever is the way by which the elimination takes place has to give the aromatic system in the final product. So, that is how the steps are actually happening here. So, in the initially, the positive charge on the nitrogen has to be neutralized. So, this particular hydrogen atom is lost as a proton unit in the first step, and this leads to the double bond formation as shown here, and afterwards the hydroxy unit is lost from the hydrogen atom from the adjacent carbon. So, this is lost as a proton unit, and this bond is now shifted between these two carbon atoms. Hydroxy unit is lost. So, we have water molecule that is lost in the final step, that leads to the tetra substituted pyrrole derivative. So, this is how the overall mechanism for this nor-pyrrole synthesis. So, we start from a dicarbonyl compound, that is ethyl acetoacetate, and the second unit is formed in situ. The amino ketone is formed in situ. If we do the same reaction in the presence of base, because in the previous one the initial step was the reaction of the carbonyl unit with the acidic reagent, that is the proton, but the same reaction can also be carried out in the presence of a base. So, in this particular case, the base abstracts a acidic proton. So, this acidic proton is lost, and we end up with an anion at this particular carbon, that is the methylene carbon is converted to the anion, and once this anion is formed, we have electrophilic carbon here. So, this attacks this electrophilic carbon, and the cyclization actually takes place, and this is the different mechanism by which the cyclization occurs in the presence of a strong base. So, whatever may be the reagent we are using, the reaction actually proceeds in different direction, but gives the same product, same pyrrole derivative as the final product. Let us look at the next one, that is a Hans pyrrole synthesis. So, here a beta keto ester is treated with a alpha haloketone, especially alpha chloroketone, in the presence of a base, that is amine. Ammonia here gives substituted pyrrole units. So, this reaction, as we have seen earlier also, the beta keto ester in the presence of a amine gives the corresponding amino derivatives. So, this is the ene unit and this is the amine unit. So, the enamine formation is the initial step, and once the enamine is formed, that enamine reacts with the alpha haloketone, and you can actually consider how the reaction actually proceeds. So, this enamine and oxygen, they first condense, and then the cyclization takes place from this particular pi bond, and this particular halogen is lost when this attacks this particular carbon. So, because this is a electrophilic carbon, chlorine is a very good leaving group. So, this cyclization occurs very readily, that leads to our final substituted pyrrole. So, the overall mechanism is actually given here, although this looks very lengthy. These reactions are very simple reactions, as you have seen. The carbonyl compound reacts with the base, that is the amino unit, to give the corresponding EMain derivative. So, this EMain is the crucial one, and once so, if we look at the ammonia reacts with the carbonyl compound, this is the first step. The lone pair of nitrogen electrons on the nitrogen attacks this carbonyl carbon. We end up with this particular intermediate. There is a proton transfer takes place from the ammonium nitrogen to the hydroxy oxygen. So, we end up with the corresponding hydroxy derivative, and this being nucleophilic in nature, abstract a proton from the ammonium ion, and then we end up with a H2O hydronium ion that is transformed on this particular carbon, and this loses water molecule very readily because hydronium ion is a very good leaving group. That leads to the formation of enamine. So, this is our initial reaction. That means, what overall thing happens is a carbonyl compound is converted to the enamine by the reaction with the ammonia. So, this is a simple reaction. So, once the enamine is formed, this enamine now attacks the second unit, that is the haloketone. So, there is a alpha haloketone, and this cyclization leads to our final product, that is the pyrrole is formed after intramolecular reactions, various cyclization, because one of the oxygen abstract the proton from the ammonium ion, and in this again abstract, that is a proton transfer actually takes place from one of the nitrogen intramolecular hydrogen transfer takes place from nitrogen to oxygen, and that leads to this particular EMain, and this loses water molecule to give the double bond as shown here, and the amino nitrogen attacks the halogen carbon internally to form the cyclization. So, as we mentioned here, the crucial cyclization takes place when the nitrogen's lone pair attacks the halogen carbon. So, this is the crucial reaction. So, that leads to the cyclization, and finally, one of the hydrogen is being abstracted by the base, and hydrogen is lost as a proton. So, a shift of bonds takes place, leading to the aromatized system, that is the pyrrole derivative. if we compare the Hans-pyrrole synthesis and the phase Benari synthesis, we have more or less the same starting materials. Say for example, we have a ketoesters, we also have a alpha chloroketone. So, in both the cases we have the chloroketone as a starting material. We also have the ketoester. In this particular Hans-pyrrole synthesis, we have the ketoester, whereas in the case of phase Benari synthesis, we have the beta ketoesters as shown here. So, both starting materials are same, but we end up with a different type of product. So, how the reaction actually proceeds? The reagent is a very crucial one. In the case of phase Benari synthesis, we are actually using a sodium hydroxide, that is Novenagel type condensation actually happens in the phase Benari synthesis, but in the case of Hans-pyrrole synthesis, the reaction steps are quite different. So, here we end up with a different substituted pyrrole, and if you look at the position, so here we have the alkyl unit present on the second carbon. Let us say if we are numbering this as 1 and this as 2, we end up with a 2 alkyl substituted compound is formed, whereas in this particular case when we talk about the furon, we are actually getting a 3 substituted derivative. So, that is the major difference between these two reactions. The use of ammonia or use of a strong base changes the product formation. So, that is how we can actually compare these two reactions, although the starting material is one and the same. In the case of beta ketoesters and alpha chloroketones are used both for Hans-pyrrole and phase Benari synthesis, but ammonia or sodium hydroxide plays a crucial role in deciding whether we end up with a pyrrole derivative or we end up with a furon derivative. And there is one reaction for thiophane synthesis. So, we have a dicarbonyl compounds reacts with thiophene carboxylic acid, especially here the 1,2-diketones as shown here. This is the 1,2-diketones. They react with dialkyl thiodiacetates in the presence of a strong base. That means we are using a sodium ethoxide as a strong base. That leads to the intermediate delta lactone formation, and this again this reaction is called as Hinsberg reaction, and in this particular case we end up with the thiophene derivatives. Let us recap in the summary what we have studied so far. We have studied the various general reactions that leads to the heterocycle formation. We studied about a nucleophilic ring closure. We also studied about a electrophilic ring closure and some of the reactions related to cyclic transition state. We studied elaborately about the individual synthesis of furon, pyrrole and thiophene. We studied the reaction mechanism of Polnar synthesis, phase Benari synthesis, commercial furon synthesis. We also studied the reaction mechanism for nor-pyrrole synthesis and Hans-pyrrole synthesis. During the session, we also studied about the various important reactions that are involved in the cyclization leading to the heterocycle formation. We also studied about what are the driving forces for aromatization. In many cases, it may be the dehydration reaction. In some cases, it may be the tautomerization or double bond migration. So, these are all the things we have studied, and we also studied about some of the crucial key reactions, that means formation of EMain, which is a very important reaction. Similarly, formation of enamines are the crucial intermediate reactions that are responsible for the heterocycle formation we have seen. And in most of the cases, the beta dicarbonyl compounds or the dicarbonyl compounds are the crucial starting materials for various furon, thiophene and pyrrole synthesis. Whenever we use a heteroatom like nitrogen or sulfur, that leads to the corresponding pyrrole or thiophene. But when we don't use these intermediates, the Polnar synthesis generally gives the furon as the major product. With that, we conclude this session. Thank you.